Jurdjevic from University of Toronto. He will speak about Hamiltonian system, an optimal control, a strong maximum principle. Thank you very much.
Well, thank you very much. It's nice to be here. I find it a little bit alarming that some of my younger colleagues are turning 65. So I feel a little bit threatened, but the reassuring thing is that they're all holding up very well. So you are certainly in that category, Jair. Keep it up, man. And thank you very much for inviting me to this festivity and sharing the occasion. Let me start with a little quotation from someone who is very well known here, Maurizio Pesciotto, who said one time to me in a very kind of offhand manner, what a pity it is that simple ideas come last. And somehow that phrase stayed with me for a long time, and somehow I thought it might be fitting for this lecture. So to orient people, to give a little bit of focus to, before I tell you what I'm going to tell you, let me start with things that everybody knows. And so what are the things that the classical canon that we all learn in school? That if we have a mechanical system, kinetic energy minus the potential energy, well, you have a mechanical system with kinetic energy and potential energy, you form the Lagrangian, and you write the Euler-Lagrange equation, and those are the equations of motion. And we have the principle of least action, that the actual motion minimizes the functional, the Lagrangian. And it's sometimes called the principle of least action, although whether you, the Euler-Lagrange equation corresponds to the critical point, as we have seen here on so many lectures. It's a critical point of this functional. Whether it optimizes or not, it's a moot point here because there's only one critical point. So, and how do we come to Hamiltonians? Well, we have a Legendre transformation, which in some situations when you can solve for the velocity in terms of the momenta, then you form your Hamiltonian, and then you have the Hamiltonian equations. So this is, everybody knows this. This is how we see things. And the Hamiltonian is the total energy, and general part of the folklore is that somehow the Hamiltonian world in the cotangent bundle is equivalent to the Lagrangian world in the tangent bundle. And you have a choice which way you like. Some people have Hamiltonian, some people are Hamiltonian, some people are Lagrangian, and you sort of coexist. And some people may not agree with this, but generally I find that people agree. So having said this, let me then ask some questions. For instance, if we go to the literature on the calculus of variations, we start with the Euler-Lagrange equation. And that's a basic object. And then sometimes you get to the Hamiltonian, sometimes not. But in physics, Hamiltonians are fundamental. So why is that? And the related question, we have the principle of least action, that's Euler-Lagrange equation. What is the corresponding principle for the Hamiltonian system? Can we start with the principle which gets us to Hamiltonian equations, rather than go Euler-Lagrange, Legendre, and go to Hamiltonian? Second question. Is every Hamiltonian, does it correspond to a Lagrangian system, vice versa? How can we do this? And then there's a Dirac famous paper on constrained Hamiltonian systems, in which you constrain somehow and you get some reduced system. And then the question is, what is the significance of this reduced system? How does it relate to the original mechanical problem? Question 3. Why is a theory of integrable systems entirely relegated to Hamiltonian systems? If they're the same, why not do something in Lagrangian? Why don't you see these things in the Lagrangian world? Okay. Question 4. What does control theory have to do with any of this anyway? And my lecture is about this, to answer this last question, to sort of say what control theory has to do with this problem. So that will be my lecture. So, as I said already, main theme of the talk is to answer the last question. me tell you, because some people here may not be so familiar with control systems. Let me tell you why the answer seems very difficult and unlikely by telling you what a control system is. So a control system, what do we have? We have a certain differential system on a manifold, which is dx dt on a manifold. X is a variable on the manifold. We have a differential system expressed by f, which depends on certain parameters called controls, u1 through um, which could be bounded in Rm, might have terrible constraints. It could consist of a few discrete points. Or it might be the entire space Rm. And then M is a smooth, usually analytic manifold, n-dimensional manifold. And then what are controls? Now, comes a very strange thing. To geometers is going to be sort of an anathema, because we require that controls be bounded measurable functions, which means that the solutions are peculiar. They are not, this equation isn't satisfied everywhere. There is Carathéodory's existence and uniqueness of solutions, which again is not discussed in differential equations. In books already differential equations, you have to go to special books to find Carathéodory, which had great vision to consider these equations. So this equation is satisfied almost everywhere and so on. So I'm telling you things already now, you're maybe a little bit put off. You say, I don't care. I don't care because I am a geometer, I am a mathematical physicist. For me, these things do not matter. Okay? So what's the basic object of study? Are the reachable sets. You have this differential system, like in dynamical systems where you have the focuses on the dynamical system. In fact, you assume that you have solutions, and you study the solutions. You don't care solve this equation. The basic objects here are going to be reachable sets. What points can you reach? If you can you reach one point to another? It's an important thing in navigation. And if you can reach them, how can you reach them in the best possible way, whatever the best is? So the prototypical example, just to mention what is the prototypical example that led to this study, is the simplest possible problem, namely a streetcar problem. Suppose that your acceleration is bounded acceleration. You want to start from here. You want to drive the streetcar to a destination. Everybody knows what the answer is. You are going to accelerate as much as you can, and you're going to decelerate at the right time so that you arrive there with zero velocity. Everybody knows what the answer is. What is the variational? What sort of calculus of variations is going to solve this problem for me? What are my variations? And people in the 50s faced this problem. In particular, was a race to the moon between the Soviets and Americans. The question was to find the right principle, which will give you the variational principle, which is going to answer this simple question. But you already see that the optimal solutions are going to be discontinuous. So you need to be in the class of, it's a large class of solutions. Okay, again, so on the surface, it looks like this has nothing to do with geometry and mechanics, because it's a very different world. And in fact, in the 50s, when all these things were discovered, that was regarded so. So in Soviet Union, where, for instance, Pontryagin, certainly a very distinguished mathematician, who discovered the maximum principle, and Arnold, who's also very distinguished, we all agree, very distinguished mathematician. You have the books on mechanics. Hamiltonian systems don't even mention the maximum principle, right? It was two worlds separate. Applied math was here, and pure math was here, and pure math speaks to God directly. Now, okay, so let me geometrize and explain how there are certain unintended consequences of this formalism. So how do measurable controls draw attention to piecewise constant controls? Naturally, because they are dense, and so it's natural to study these objects. So control system, then, if I pass to piecewise constant controls, For each piecewise constant control, there's a fixed vector field. So my control system now becomes a family of vector fields. Okay? Oh, sorry, going backwards. And then if I look at trajectory, which corresponds to piecewise constant control, consists of diffeomorphisms, if these are one-parameter groups induced by the vector fields. And I see that it's a concatenation of a trajectory, which corresponds to piecewise constant control, is a concatenation of one group vector fields, one group of diffeomorphism, with one caveat, namely that you are moving in forward time. You cannot go backwards in time. You cannot correct for your mistakes. You're moving always forward. So you're moving in a sort of certain direction, if you will. So that tells you, you already see that it's going to be, you can concatenate these diffeomorphisms at your will, providing that the time is positive, that is, that you are moving along semi-orbits, positive orbits. So that sort of gives you a certain action of a semi-group of diffeomorphisms on your space. The natural object is the group of diffeomorphisms. That's a natural object. So you look, your family of vector fields, your control system now is a family of vector fields. You look at the group of diffeomorphisms generated by piecewise constant controls. So that's an infinite dimensional group and all that. The remarkable fact, so the semigroup, when is a semigroup equal to the group? Well, if it has certain symmetries. If your u's, you can reverse a u, your control, and then reverse the time, and somehow then two objects are the same. And in many situations, that will be the case. So already we have a nice geometric object. And the remarkable theorem, so then we have the orbits. We have a group of diffeomorphisms. So we have natural orbits. And we look at the orbit through a point. And the remarkable thing that under no assumptions whatsoever, the orbit, each orbit is a submanifold, has a manifold structure. Under no assumptions whatsoever. So if you're in CK vector fields, it's a CK manifold. And if you're C infinity, it's a C infinity manifold. And if you're in an analytic case, it's an analytic manifold. So now you have that the reachable set from a point x0, that the action of the semigroup sits inside of the reachable sets, sits inside of the group, inside of the orbit under the group, which is a manifold. And now the natural question is, and by the way, this is a very interesting theorem, which applications, unintended certain application of this, is in geometry. But I'll come to this point in a moment. So far, that's what we have. So what is the relation of the family F of the vector fields to the dimension of this orbit? Which vector fields are tangent to, what is the dimension of this orbit? And it's easy to see that each vector field in the family F is tangent because the orbit is defined by these vector fields F. So each member in the family is tangent to the orbit. So Lie algebra generated by these vector fields is tangent to the orbit. So we are making contact. Now suddenly, our control system is making contact with the work of Sophus Lie. And so well, I came up with this definition. I said F is Lie determined if the Lie algebra, the evaluation of the Lie algebra at each point coincides with the tangent space, fills up the tangent space of the orbit. Okay, so for instance, if you have, it's not always the case. In the C infinity case, that may not be so. Take two vector fields, one which is two vector fields which are the same here, but the other one is like that here. So you can start from here, you can go to, well, these vector fields, yeah, one of them is straight, so I forget exactly how to do it, but somehow you can go to here and then you can come back here, so you can move in this direction, even though the Lie algebra here is one-dimensional, but the Lie algebra here is two-dimensional. Okay, so you can go, the orbit would be the entire space, even though these two vector fields are collinear here. Oh, this is upside down. Is it? So I call it Lie determined. So in fact, if the Lie algebra is a full rank at each point, then the orbit is open. And the Hermann-Nagano theorem says that if you have analytic vector fields, then they're Lie determined. That is to say that the orbit, the dimension of each orbit, coincides with the rank of the Lie algebra at each point. It doesn't say this is, so these orbits could be of different dimensions. So for instance, there are two beautiful applications of this theorem. One is a theorem that a closed subgroup of a Lie group is a Lie group itself. It's an immediate consequence of this, because you just look at the vector fields whose tangents are in the group, you look at the corresponding orbit, it's a subgroup, and you prove this almost immediate consequence. The second one is a beautiful thing that was already mentioned here, which I think it's Allen's theorem, that if you have a Poisson manifold and you have Hamiltonian vector fields on the Poisson manifold, then it's foliated by symplectic leaves. Well, here take the family of vector fields which are Hamiltonian or Poisson manifold. The only thing that you have to prove that it's Lie determined, that is to say that the dimension is the same. And that you prove easily. And it follows then that each orbit is symplectic manifold. And again, it will be an easy application. All right. So how does this relate to control problem? Again, this is sort of generated by control problem. So now, let me come back to really problems of control, and before I come to Hamiltonians. So let me just introduce some notation and start talking about topological properties of reachable sets. One of them certainly is the interior, which is the important part, and the other is the boundary. So what can we say about these objects? The accessibility theorem, there's something, this is 1970s. If you have a family of vector fields which is Lie determined, let's say here for the purposes of this lecture that everything is analytic, so everything is Lie determined. So the Lie algebra being of full rank is a necessary and sufficient condition for the interior to be non-empty. And in fact, if the interior is non-empty, then the interior points are dense in the reachable sets. So we have a nice algebraic object. You know that your reachable set is going to be open. You're going to be able to go to an open neighborhood just by evaluating an algebraic object, evaluating the rank of a certain algebraic object, namely the Lie algebra. So you don't have to solve your equation, which you cannot. Okay. Now, the reachable set need not be, because this is a very general theorem, the reachable set needn't be closed. So it's, mathematically speaking, it's natural to close the set and work relative to the closure. And in fact, that's the idea behind a concept that Kupka and I created in, well, working controllability. Somehow it came natural. It came to define the Lie saturate of a set, or a family of vector fields, which is somehow the most natural, the largest family in the Lie algebra, whose reachable sets up to a closure with the original set are the same. And that would include all the symmetries of the system. So, you see, there's a subtle point here, that suppose that you have one vector field on the torus whose orbit is dense. If you close it, it's in the entire space. If you look at the set of things which are equivalent to it, it would be all of every vector field. So it's a huge discontinuity. But you require, if you require that in the Lie saturate, that your vector fields in the saturated family are in the Lie algebra generated by F. If you have one vector field, then the Lie algebra generated by that is just the field itself. So it prevents this pathology. And for instance, among other things, you cannot have, under the conditions that the Lie algebras of full rank, you cannot reach a dense set of the manifold without reaching every point. So now, the Lie saturated, there are some properties that we discovered. Namely, you can convexify, you can include all the symmetries of the system, and it's natural to work with this Lie saturated. Of course, in principle, you don't know how to find it, but you can at least do some simple operations which help. Depends what you want to do, of course. And yeah, what did I want to say here? Yeah, I don't know. I don't want to make a remark about this, but for instance, in particular, if you have a symmetry, as you notice here, something a vector field whose leaves the reachable sets invariant up to a closure, then you can also form the Lie brackets with the Lie saturated is going to be the Lie saturated. So this is the closure also. It's a convenient object. So now so the rank of the Lie algebra relates to the interior. Let's look at the boundary. What are the trajectories which reach the boundary? And I come to the Hamiltonians here. And this is really, most people are interested in that. So I'm coming to this point. We just have a little bit of patience. So you call a trajectory of your family of, yes, the point that I wanted to make is that the Lie saturated, closing things under, if you have a family of vector fields, like two vector fields, you can form their, look at the convex cone generated by it. That's good to convexify the system. And that sort of comes back to the central theme of this, perhaps one of the central themes of this talk, is that a family of vector fields and a control system, it's one and the same object. Family of vector fields, if you want to study reachable sets, you can convexify, you can then pass on to some reasonable differential system in which the parameters which in the convexification you call controls. So two objects are the same. So, all right, so you want to go to the boundary. And so what does it have to do with optimality? I come now to optimal control problems. Suppose that we have a differential system, a control system, you want to minimize some kind of functional, whatever it is, given by a function f. And you have the boundary conditions. Now there are two kinds of optimality problems that you can ask. One is, can I go from here to here in 1 second? 1 second is fixed. And the other is, can I minimize this functional over all possible time? Namely, I look at all the trajectory which get me from one point to another, and I look at the minimum. For instance, in the least possible time. How do I go from here to here in the shortest possible time? So there are two problems associated with this. Now, the maximum principle, or if you like, now I'm coming back to Hamiltonian formalism, we can formulate this as a problem reaching the boundary. Because if we now consider the extended system where, in addition to your dynamics of the system, you attach the cost, the functional that you want to minimize. And then it's easy to see that if you want to be, if the trajectory which is optimal above has to be on the boundary of this extended set. So now comes the question, what are some necessary conditions that a point be on the boundary of the reachable set? And if we're on the second problem, that is to say, the terminal time is fixed, then we have to extend the system by one more parameter so that it becomes, so that time is the parameter. So the only way that you can reach a point in this extended space is if the time is exactly the time that you require. So all these problems are more or less the same. So now we come to Hamiltonians associated with these problems. So to repeat, to go to the boundary, now I somehow find necessary conditions, that's Pontiagin, that is in terms of Hamiltonian systems. And then, having told you that, then we'll come back to Lagrangian and Hamiltonian to explain what's the connection, and then go on to the strong maximum principle. Okay? So now, again, things which everybody knows here. And maybe everything that I said so far, everybody knew already. But then it's good to hear this thing again. Okay. So we go to the cotangent bundle of the manifolds, and instead of using points which, denoting these points by two variables, I'll just denote them by single letter chi. And pi is a natural projection, which drops it down from the cotangent bundle to the ambient space. And in the canonical coordinates, psi would be the x and the momentum. And if we have a function on the cotangent bundle, I denote it by h arrow is the Hamiltonian vector field. So now, if we have a vector field downstairs, every vector field downstairs of the manifold M can be lifted to a function on the cotangent bundle. Namely, there's a natural evaluation here, which I'm sure everybody knows here. And then I look at the corresponding vector field, Hamiltonian vector field. So every vector field downstairs has a natural lift to a Hamiltonian vector field upstairs. And in particular, my family F, my control system, which I started with, can be lifts to a family of Hamiltonian, or if you like, lifts to a family of Hamiltonian vector fields. And then there are trajectories in the family above, and every trajectory above projects onto a trajectory downstairs, and every trajectory downstairs is the projection of a curve upstairs. I've just wrote down just what I told you, that there is a kind of correspondence between things downstairs and the vector fields above. So now the maximum principle, what is it based on? It's based on the fact that if a trajectory goes to the boundary, then the variational equation, whatever that is, I will not be able to talk about variational equation. It's an interesting equation because if you understand what the variations are, then you would immediately see where the strong maximum principle comes, which, again, I think it's very useful. And that's the really sort of principal point of my talk, because that's something which I think is relatively new. But anyway, whatever it is, if you're on the boundary, then the associated variational system has to be singular at this point. Because otherwise, by some implicit function theorem or Brouwer fixed point theorem or something, it's going to be, otherwise the point would be in the interior, sort of like implicit function theorem. So what does the maximum principle say? If you want to go to the boundary, suppose you have a trajectory which takes you to the boundary and reaches time t, gets to the boundary of the reachable set, then this trajectory is necessarily the projection of a non-zero integral curve of the family of vector fields, Hamiltonian vector fields above, that you lifted it to, with certain properties. That the Hamiltonian along your optimal trajectory, well, in the case that time is not fixed, then the Hamiltonian along this optimal, along this trajectory is equal to 0, and relative to this control, u bar is the control which takes you to the boundary, and this Hamiltonian is optimal, is maximal, because all the others are negative, less or equal than 0. And in the second version, if you had a fixed time interval, then these two statements are almost indistinguishable, except that in the second statement, the Hamiltonian along this optimal control is constant on interval 0t as opposed to being 0, and then each other trajectory, each other corresponding to each other control, the Hamiltonians have to be less or equal than 0. Hence the name maximum principle. So it admits a very nice geometric interpretation. That is to say that if you want to go optimally, if you want to go to the boundary, in your family of Hamiltonians above, you have to choose Hamiltonian which is kind of maximal, because your Hamiltonians above are parametrized by controls, and you have to choose a control which is somehow maximal in this family of Hamiltonian. And if we now go to the optimal control problem, we have this extended system, and now comes sort of, we see sort of peculiarities certain, which appear, which for people who are steeped in mechanics and geometry do not see. Namely, that the multiplier, that is to say that the dual variable, which is now in the extended space, because the extended space, in the cotangent bundle of the extended space, the space is m cross r, because we extended it by the cost, has to have a multiplier in front. The corresponding, the dual variable has to be then in the dimension, appropriate dimension. So the cost is, so if you will, the dynamics in this extended system are not of the same rank, so to speak. One is the dynamics of the system, and the other is how much does it cost you to get there. So they have sort of different values, if you will. So there is multiplier size 0 in front of the cost. And it turns out that this multiplier has to be constant because the corresponding variable is a cyclic variable. So it has to be constant. And then because of the maximum, it has to be, let's see, maybe I'm getting ahead of myself. Yeah, so again, I'm just repeating what the maximum principle says that about the boundary. And so, well, it's completely analogous. I'm just repeating this, I don't know why. And so, to go to the boundary and to pass to the problems of optimality, come some interesting facts. That this multiplier in front of the cost, if it's non-zero, then it can be normalized, so it's -1. And the corresponding projection of the curve is called the normal extremal. And the ones which correspond to size 0 equal to 0 are called abnormal. And this is something which doesn't appear in problems of mechanics, because if the family of the vector fields is such that its linear span spans all of the tangent space, then there are no abnormal extremals. So we are in the classical situations. And there is some mystery about these abnormal extremals. And in fact, Richard here is the one who's, we all know Richard's example, in which the first one which really stirs some controversy. But see, it's not surprising that these abnormal extremals are going to appear, because you could be on the boundary. See, for the problems, well, I'll maybe make some points, that this is really sort of expected, because you can be on the boundary for a number of reasons if your control system is such that it's, for instance, you have very few vector fields, so you have to rely on the Lie brackets to get you to go everywhere. So you could be on the boundary for a number of reasons. Some of them are because you are optimal. Some of them are just because your boundary consists of other points. So then those points will be solutions of your Hamiltonian systems. Doesn't matter what kind of cost you put on it. So it's independent of the cost. So it's an interesting phenomenon that occurs. So let's come back to the calculus of variations to the original problem we started with. Suppose you have a Lagrangian, you want to minimize it. What is the control problem? Now, in the calculus of variations, there is also, okay. In the calculus of variations, there's an interesting thing which is very often sort of hidden, if you will. Because there are two versions. A weak version, you consider minimum over continuously differentiable curves, and strong version of the Lipschitzian curves that satisfy. So, Kara Theodori, for instance, in his book, dwells upon this point to a great deal, a lot, where some of the modern books just forget this point whatsoever. And you see in Kara Theodori's book, there's a problem to interpret the Weierstrass's conditions, because he doesn't have the maximum principle at that point. And if you look, he tries really hard to incorporate, but he doesn't have the tools. So it's kind of left hanging, if you will. Okay, so passage to control. Now you pick any frame. Any frame on your system defines a control system, because every curve now can be written as a solution of your control system. Now it's artificial, I admit, because you choose a frame. It's dependent on the frame. So if you choose a different frame, you have a different control system. But it turns out that all these systems are equivalent. So then if you pick a system, if you pick a frame, then the frame induces its corresponding cost, namely your kinetic energy, then it's going to be a quadratic form, positive definite quadratic form on the controls, and you have the potential function, and Q depends on the choice of the frame, and you then optimize according to the prescription that maximum principle tells you, and you provide the first answer, which I asked before at the beginning of the lecture, that the principle, the Hamiltonian principle, which corresponds to the principle of least action, is the maximum principle. Is the maximum principle. So you don't have to go to Euler-Lagrange equation. And by the way, to go to Euler-Lagrange equation, second-order differential equation, the manifold, you need a connection to write it. Here you don't have to. You bypass it. Of course, this is dependent on the choice of frame, and then the extremal controls are going to be, and then the rest of the mathematics is the same as you find in the classical books. You solve for this is your Legendre transformation, and it turns out in the proof of the maximum principle, the Legendre transformation is already embedded in the proof. And then you get your Hamiltonian, it's going to be sum of the energies, the usual thing, and so the maximum principle, as I just said, the maximum principle is the Hamiltonian that corresponds to the principle of least action. And if you use the canonical frame, E1 through En, the extremal equations are exactly the solution you solve for the momenta in terms of the Legendre, in terms of the velocity, generalized velocity. And then it turns out that Weierstrass, an excess function, is exactly the maximum principle. So, see, this kind of unifies. It tells you in a very nice way the Hamiltonian system, how to get to the Hamiltonian system. Again, your choice of frame is sometimes, there are many choices. For instance, if your system has certain symmetries, you're not going to use the canonical frame, the usual frame of the translations in the ambient space. It's much more intelligent to use some other frames. Like, for instance, on the ellipsoid, you're going to use, if you were doing geodesic problem on the ellipsoid, Jacobi's famous problem, you would use elliptic coordinates, and you would use there will be different kind of equations. But in principle, you're always doing the same thing. Now I come to the strong maximum principle. What is that? Come to the strong maximum principle. So some general remark. The problems of Riemannian geometry or mechanics, the boundary of the extended reachable set consists of optimal solutions only. But in the more general case, for optimal problems, that's not the fact. And in fact, if the interior of the reachable set is empty, if you didn't know that the reachable set has a non-empty interior, then the maximum principle wouldn't say anything. Because every trajectory is extremal because it goes to the boundary, because there's no interior. So the maximum principle, it's very important to realize, it's not stated in most books, that really the Lie condition, Lie algebra condition, and the maximum principle are really two statements which go hand in hand together. Now, the strong maximum principle, it's almost the same thing as the original principle, except that instead of your Hamiltonian, again, it's equal to 0, corresponding to a trajectory which takes you to the boundary. But then it turns out, again, the proof is pretty much the same, that the Hamiltonian is not only optimal relative to the family F, but in fact to the saturated family. It has to be optimal too. which is a much larger family, which in principle you don't know what it is, but still, if you happen to know what are some symmetries of the system, then you can immediately exploit that. So in particular, what it says, that if you have a vector field, which is in the Lie saturate, which is both plus and minus are in the saturate, then necessarily the Hamiltonian along an extremal curve has to be equal to 0. That is to say that it has to be constant of motion of the system. And again, there's an analogous version for the fixed time interval, and you just have to replace the Lie saturate with a strong Lie saturate. That's something which is explained in my book, so I can find it. And the corollary is Noether's theorem follows immediately from the strong maximum principle. And so if you have a symmetry for the control system, you have to, and the symmetry just preserve the reachable set, then the corresponding Hamiltonian is constant along every extremal curve. For the problems of the calculus of variation, you don't have to worry about the reachable set, so it's just a symmetry if it leaves the Lagrangian invariant. But here you have to worry about also the reachable set. But the conclusion is the same, and it follows from the maximum principle. And the proof is, again, very simple. If you have plus minus, as I mentioned before, if it's a symmetry, then the Lie bracket has to be in the Lie saturate, and then you differentiate the Hamiltonian corresponding to the symmetry, and just using the standard calculation, using Poisson brackets, you get that it's equal to 0. That's a 3-line proof. Okay. Now let me move on to the moment map now. That's a close companion. And I claim also that the moment map, it also follows very naturally from this strong maximum principle. It's a direct consequence, in fact. So now suppose that I have a symmetry group for the system. So if I have a symmetry group, then the corresponding induces the corresponding diffeomorphisms on the manifold M. And you have a family of vector fields which are induced by this action on the manifold. I call this family of vector fields subordinate to the group action. So they're induced, and most people here know that. So it's an induced family on the manifold, induced family of vector fields. So G is a symmetry group, just obvious thing, if in fact leaves the invariant sets invariant. And that means that the Hamiltonian, and then I look at the Hamiltonian lifts of the vector fields which are subordinate to the group action, and according to the strong maximum principle, they're all constant. They're all constant along the extremals of your system. And the rest is as you would find it in the books of integrable systems. For instance, Bariloche's book. The mapping which takes an element in the Lie algebra to the corresponding Hamiltonian function, Hamiltonian lift of the induced vector field, is linear. So that's a linear function. It belongs to, you can identify it with a dual in the Lie algebra, of the dual of the Lie algebra. And the mapping which takes you from the cotangent boundary from the duals into, psi are points in the cotangent bundle which take you to the linear function. It's called the moment map. And we see that this moment map is constant along the extremal curves along the extremals of my system. And then if you happen to have a non-degenerate quadratic form on the Lie algebra, then you can identify elements of the dual with the Lie algebra, and the spectral invariants of this matrix then are constants of motion for your system. So what I'm saying is that all of things which we know from classical symplectic geometry and all this stuff, can be seen in a natural way by extending our understanding of Hamiltonian systems and all this through, I think, control theoretic insights. And for instance, okay, so I have a couple of minutes. Maybe I finish early. Well, it would be maybe too much to start talking about particular systems now. For instance, Dubin's Delaunay problem of finding the shortest curve with prescribed bound on the curvature that connects two given tangential direction is, for instance, one can prove that it's completely integrable in any dimension. A very nice thing, which really uses these ingredients and comes in an elegant way. You prove it's completely integrable in the usual sense. Also, there's another way that you can apply all this theory, and I'm very sort of pleased with this result because it goes back to Jacobi's problem, geodesic problem on the ellipsoid. And this problem is fascinating because, as many people wondered about, why is this problem integrable? Because it doesn't have any obvious symmetries. And it turns out that actually you can find these symmetries by lifting it to a Lie group. And, well, I'm getting ahead of myself. So let me just see what... Yeah, I wanted to also say that this kind of symmetry, employing these symmetries, you naturally fall on co-adjoint orbits also. It follows, it's sort of a consequence of the moment map, which I just explained. So in particular, it applies to system on Lie groups. So for instance, suppose that you want to minimize something which depends over a left invariant control system. Doesn't matter what it is. And it's left invariant because the cost, you see, depends only on the control, U. And you can easily see that you can start with a family of vector fields, left invariant vector fields on the family, on a Lie group, and consider the corresponding system. And you want to maybe ask some question, what are the curves of shortest length, or something like that. Ask a generalized sub-Riemannian problem or something like that on a Lie group. And in particular, this applies to sort of the Kirchhoff's elastic rod models, Euler-Griffith's elastic problem, etc. And because the problem is left invariant, there's a group of left invariant symmetry which acts on it, and you apply the moment map. I think, you know, maybe I've said already too much. It turns out that left invariant vector fields, well, this implies that right invariant vector fields are going to be symmetries because right invariant vector fields commute with left invariant vector fields. And immediately follows from the moment map that the Hamiltonians, which correspond to the right invariant vector fields, in the left invariant trivialization are going to be constants of motion. And that means that the dual variable L of t is going to live on the coadjoint orbit. I'm sorry, I've gone through this a little bit too fast because I feel that somehow I've said already a lot and I get a little bit tired. So you immediately fall, if you're left invariant from left invariant symmetries, again, your solutions are evolved on coadjoint orbit, and then you fall into the vast literature on integrable systems by Mishenko, Fomenko, Arnold, and so on. And in particular, to come back just to finish as what I was saying, to see the symmetries of the Jacobi's problem, symmetries, sorry, I'll just conclude, which is a little bit slightly off the point, but it relates to this. Jacobi's problem, so rather than study Jacobi's problem as it was given by Jacobi, I found an equivalent way to look at Jacobi's problem by slightly twisting things, being on the sphere rather than on the ellipsoid, but having elliptic metric. And if you study this problem, and everybody can see that that problem is going to be equivalent to Jacobi's problem, whether you have a metric which is from the ambient space, Euclidean metric on the ellipsoid, or whether you're on the sphere and you have elliptic metric, they're going to be the similar problems. But what's the advantage of this? The advantage of this, what Tudor knows very well, that the cotangent bundle of the sphere is a co-adjoint orbit on the group of symmetric matrices relative to some semi-direct product. And when you lift this problem above, you see that this corresponds to a control problem on the SLN, which has spectral representation from which Jacobi's integrals of motion appear as spectral invariants. And that explains the symmetry. There are certain symmetries which you only see on the Lie group. And anyway, that's my talk. And thank you very much for your attention.
Well, we have time for some